Today we're going to be solving the CIE AS Chemistry 9701, October-November 2025, paper 31. So, we are meant to read the whole method before starting any of our practical work and to prepare a table of results where necessary. We must show the position of the apparatus used. This is through our units and our decimal places. And we should also show any working out and appropriate significant figures. Again, just to show or contributes to the precision in the final answer to each step of your calculations. The final answer. It says here that hydrated ethanoic acid is a diprotic acid. So basically it has two functional groups, two carboxylic acid functional groups, and it's given the following formula where X is an integer. Ethanoic acid reacts with manganate ions when heated. This is the following equation, and we are meant to determine the value of X by titrating a solution containing the ethanoic acid with manganate ions. Now the method is as follows. Fill the burette with Fa2. Our Fa2 here is our potassium manganate, right? And it's of 0.02 moles per decimeters cubed, okay? It then says to pipette 25 centimeters cubed of Fa1 into a conical flask. Our Fa1 is our ethanoic acid. So there'll be, I'll just write the formula, COOH 2.XH2, and 25 centimeters of that into our conical flask, okay? It then says to use a measuring cylinder to add approximately 20 centimeters cubed of Fa3 to the conical flask. Our Fa3 is our 1 mole per decimeters cubed of our sulfuric acid. It then says to place the conical flask onto a tripod and gauze and heat until the temperature is approximately 70 degrees Celsius. So here is our tripod. This is our flame. It's really a Bunsen burner. And then we would measure, we just keep heating until, if we had a thermometer inside, for example, it reached 70 degrees Celsius. And then we would remove the flame. So then it says to carefully lift the hot conical flask and place it onto a white tile. Okay, so this would be our white tile. And we'll talk about why we use a white tile in a second. It then says to add Fa2, which is our potassium manganate, for the first 2 to 3 centimeters cubed drop-wise. So not using a dropper, rather using the burette. Our first 2 to 3 centimeters, and then we just keep adding. This is until we get a permanent pink color. So any initial pink coloring may take several seconds to disappear. This is not our final result. We should wait for it to disappear, and then we keep adding, okay? If the reaction mixture just turned brown, you need to reheat it, and if the color disappears, we can continue. If it remains, then we have to discard the contents and then just begin a new titration. Our end point is when there is a permanent pale pink color. Now, we use this white tile so that the color is visible. And then it says to perform a rough titration with Fa2 and then to record our burette readings in the space below. So this is our rough titration. We have our ethanoic acid reacting with our sulfuric acid, but also our manganate ions to produce this color change. And from that, we can determine the value of X eventually. They've told us to carry out as many titrations as we think necessary to obtain consistent results. Make sure any recorded results show the precision of your practical work. Record all your burette readings and the volumes of Fa2 added in each accurate titration. So I'm just going to use realistic values. For the rough titer, I'm going to put down that I got 34 0.6 centimeters cubed. I'm actually going to make this to 2 decimal places. Okay, so I've generated a table of results. We're going to look at what our marks would be for. So our first mark is for having 2 burette readings, an initial and a final, as well as a titer volume for the rough titration, as well as for 2 or more other titrations, okay? Our second mark is for having titer values recorded for accurate titrations, as well as having correct headings and units. Don't forget your units. There must be an initial and burette reading or volume. So really, you must use the term reading or volume. I have written just burette, just to like, just to do it faster, but really, burette in the mark scheme is actually in brackets, so it isn't necessary to obtain the mark. However, you would need to mention reading or volume, and then you do that for final, and then you also need to have a titer volume, or you could say FA2 added, centimeters cubed, and obviously a mark for the units. This is all for mark 2, okay? Mark 3 is for all your accurate burette readings to be within, recorded to the nearest 0.05 centimeters cubed. So as you can see, all of our units end in either 0.0 or 0.05. Or point something 0 or point something 0.5. Then our fourth mark is for all the final accurate titers recorded being within 0.1 centimeters cubed of any other accurate titer. Okay, so I've just put a rough titer value of 24.80 centimeters cubed. A rough titer is basically your first titer. It tends to be not as accurate as your other results just because it's your first trial. And then if we head down here, I've just generated a table of realistic results. We're just going to go through the marking points of our table. So what you needed to do to get these marks. So for mark number 1, what you needed was to have 2 burette readings, the initial burette, the final burette reading, and the rough titer columns. And you needed to have 2 or more readings, so I did 4 trials, the first being the rough one. For the second mark, you needed to have an initial and a final burette reading. By the way, burette in the mark scheme is in brackets, so you don't get the mark for just saying that. You must say reading or volume. I've only written burette just to save space because I'm doing this on a device. However, in real life on paper, you should be able to fit in all of this together. You also must use the correct values, the centimeters cubed for each. Don't forget to add your units to your columns, and to obviously state that the titer volume or FA2 added. If you want to change your wording, that's fine as well. That's for mark 2. Mark 3 is for all accurate burette readings to be recorded to 0.05 centimeters cubed. So to 2 decimal places, round up, round down to the nearest 0.05 centimeters cubed. For mark 4, you needed your final accurate titer recorded to be within 0.1 centimeters cubed of any other titer. So really, if we look at my last 3, it could be just 2 or it could be more. They all have to be within 0.1 centimeters cubed of each other for accuracy reasons. And then we have marks 5 to 7. This is really dependent on how similar your results are to the supervisor who will carry out the experiment themselves results. Now, there's also a hierarchy in terms of determining your accurate titers. If you have 2 identical ones, you go with that. If not, the second best option is to go with those that are within 0.05 centimeters cubed. If not, then those that are within 0.1 centimeters cubed. Anything beyond that is probably not accurate enough. It would be best to repeat a titer if you have enough time. Also, just to be wary, when you are reading off of a burette, remember the scale goes down, unlike measuring cylinders and the sort. The zero is at the top, and then the graduations increase as you go downwards. So this is especially important if you're reading between the numbers. It can be really easy for you to mess up and count backwards, in a sense. So just be careful when reading burette values. Okay, now question B says that from your accurate titration results, find a suitable mean. Like I said, these last three are all within 0.1 centimeters cubed of each other equally. So I'm just going to take the mean of that. To be honest, really, as you can see, 24.6 is in the middle, so it's the mean value. But really, what this would entail is adding up your values and then dividing by whichever values are, dividing by the number of those values. So we end up with 24.60 centimeters cubed. That is, it needs to be to 2 decimal places because that's how accurate a burette is, and you have to show you're working out or like put ticks near your accurate titers. So just an indication as to where you're getting these values from. And yeah. Okay, now it's asking us to carry out a few calculations and to give our answers to the appropriate number of significant figures. The appropriate number of significant figures accepted by the mark scheme are anything from 3 to 4 significant figures, okay? Okie dokie. So, let us begin. Question number 1 asks us to calculate the number of moles of manganate ions in the volume that we had of Fa2 added. So Fa2 was our manganate, our potassium manganate. So the volume we had added, well, the concentration that we used was 0.02 moles per decimeters cubed. And the volume that we added, or the titer volume we ended up with was 24.60 centimeters cubed. Really, we know that moles equals concentration times volume. This is our concentration. This is our volume. So all we need to do is we need to multiply them together. But remember, 24.60 centimeters cubed is not in decimeters cubed. And that's what our concentration is in. So you need to divide by 1,000 before we multiply them together. So really, when we multiply these two together, we end up with 4.92 times 10 to the negative 4 moles. Then it says calculate the moles in ethane dioic acid. Now we need to look at the molar ratio. If we go up, we can see that for every 2 moles of manganate ions, 5 moles of our ethane dioic acid react. So they are in what we call a 5:2 molar ratio. That means it's 5/2 times more moles of ethane dioic acid. So 5/2 times 4.92 times 10 to the negative 4 is equal to 1.23 times 10 to the negative 3. Okie dokie. It then says to hence calculate the concentration. The concentration is going to be the moles divided by the volume. The volume we used was 25 centimeters cubed. Up here we used a pipette to add 25 centimeters cubed of this acid. So really what we should be doing here is our moles, which is 1.23 times 10 to the negative 3, divided by our volume, and then that volume divided by 1,000, because remember, we need to go from centimeters cubed to decimeters cubed. This is equivalent to 0.0492 to 3 significant figures. Then it asks us to calculate the relative molecular mass. Now, MR is equal to mass divided moles. We have 6.2 grams divided by decimeters cubed. We have 0.0492 moles divide our decimeters cubed. So really, our decimeters cubed are going to cancel out. and we need to divide by this. Because dividing by this, and I'll show you how the decimeters cubed cancel out, is equivalent to 6.2 grams times over 0.0492. So these two cancel out, and we're really just doing 6.2 divided by 0.0492, which gives us an MR value of 126. And this, okay? And now finally, we have to calculate our value of X. So if the whole of this compound has an MR of 126, and we know that water has an MR of 18, and our double COOH groups have an total MR of 90, really, when we do 126 minus our 90, we get 36. So XH2O equals 36. In other words, 18X equals 36. In other words, X equals 36 divided 18, which is equivalent to 2. So really, our value of X here is 2. Lastly, it asks us to explain why we added Fa3 into the titration. Fa3 here was our sulfuric acid. Now, if we look at the equation, besides the manganate ions and the ethylene dioic acid, we have hydrogen ions in the equation. So in order to provide these hydrogen ions, which are vital to the equation for it to take place, we need something that will donate protons. What donates protons? Acids. So we use sulfuric acids. So all we really need to say here is that H plus is needed for the reaction. Now on to the second part. So it says here that hydrated zinc sulfate has the following formula, where Y is an integer, and it actually decomposes when it's heated, only losing its water of crystallization, becoming anhydrous. So what we're going to do is we're going to carry out an experiment to determine the value of Y by heating the hydrated salt until it becomes anhydrous. We're using Fa4 to represent the hydrated zinc sulfate. Now the method is as follows. Weigh the crucible with its lid and record the mass. So here's the crucible, lid, and our scale. Add around 3.2 grams to 3.4 grams of our hydrated zinc sulfate to the crucible. So we're going to add 3.2 to 3.4 grams of our Fa4. And then we're going to reweigh with its lid and record the mass once again. Then we're going to place the crucible on the pipe clay triangle and gently heat the crucible for around 2 minutes with the lid on. Okay? So pipe clay triangle, like around here. And then we have our lid on. For 2 minutes, we're going to keep it on a low flame, so yellow or light blue flame in the Bunsen burner. Then it says we're going to remove the lid and then heat the crucible strongly for approximately 4 minutes. So we're going to switch to a blue flame, a roaring blue flame, which is much stronger. Keep it on there for 4 minutes. There will be no lid. Then it says replace the lid and leave it to cool for at least 5 minutes. So for 5 minutes or more, you keep it to cool with its lid on. It says you can work on question 3 while the crucible is cooling. After you leave it to cool, you're going to weigh the crucible and its contents with the lid once again. Record the mass. Remove the lid. Heat strongly for approximately 3 minutes. Then replace the lid. And then let it cool. And then reweigh it. And then record the mass. So really we're just going to be heating strongly, waiting for it to cool, recording the mass. Heating strongly, waiting for it to cool, recording the mass. Each time with the lid on so that we are not altering our results. Then calculate the mass of Fa4 used and the mass of residue obtained. Sorry, to calculate these and then record the masses. So I've generated a table of results. To gain the first mark, what you needed to do is you needed to have 6 correct headings. I knew to have these headings because I noted every time it say record or calculate. So it says record here, 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 and it says calculate here and here. In total, there are 6 values, so I should have 6 headings. Must mention that it is the crucible plus the lid each time. And we also need to make sure that we have mentioned the units in every single one. And that would be grams, obviously. Then for our second mark, we need our 4 readings. These 4, because the last 2 are calculated. And they have to be to the same number of decimal spaces. They have to be either 2 to 3 decimal spaces, and they all have to be, if they're either all 2 or they're all 3. And then we also have to make sure that reading number 2, our second reading, is within 0.02 of the first reading. And negative 0.05 of the reading of the first reading. Okay, so within that range. And then for our third mark, we need to have had correct subtractions for our residual mass, for our mass of Fa4 and residue. And the mass of Fa4 needed to be between 2.9 to 3.4 grams. And then marks 4 and 5 are accuracy marks. They'll compare your results to the supervisors to see how similar your results are to each other. The more similar, the more likely you are to get both marks. Just to briefly touch up on this bit a little more. What this essentially means is the reading after the second heating should be no more than 0.02 grams higher than the first than the first mass, and no more than 0.05 grams lower than the first mass. So there should be little difference between the two. Now we move on to the calculation section. The first thing they want us to calculate is the moles of anhydrous zinc sulfate. This is our residue, because remember what we did is we heated it so that all the water would evaporate and we're only left with the anhydrous substance, the residue. So our residue value was 1.8 grams right here. And we know that the MR, by just summing up the atomic masses of the individual atoms in the compound, is 161.5. The number of moles is equal to the mass divided the MR. So really, the number of moles here would be equal to our mass, 1.8, divide 161.5, which would be equivalent to 0.0111. Any answers from 2 to 4 significant figures are acceptable. Then it says to calculate the amount of moles of water of crystallization loss. So the water lost, how would we calculate the mass of that? Well, if we know that initially we had hydrated and then it became anhydrous, the mass lost is the mass of water lost. So really, the mass of H2O lost is our 3.2 minus our 1.8, because the hydrated substance, our Fa4, was 3.2 grams from our table. So, okay, which would give us 1.4. And then to calculate the moles, we know the MR of H2O is 18. So 1.4 divide 18. equivalent to 0.0778. It then says calculate the value of Y in the formula. So we have the moles of each. We can calculate them because they're in ratios to each other. We know that there's 1 zinc sulfate for YH2O. So what we can do is the moles of H2O, 0.0778, divided by the moles of 0. Okay, because really, if you look at it, 1, the ratio represents 0.011 moles. Y represents 0.0778. And then we cross multiply. We will get a value of 7. So Y equals 7. Then it says to suggest Y using thermal decomposition method to investigate the number of moles of water of crystallization. Hydrated ethanedioic acid is a non-suitable method. Well, if you think about it, the acid would probably decompose upon heating. But another reason why this is probably not the best thing to do is because acids are flammable. This would pose a hazard risk. For the qualitative analysis part, you're going to record your observations for all the tests you conduct, mention any color changes seen, formations of any precipitates and solubilities where appropriate in excess of reagents, the formation of any gas and their identifications, and at what stage these observations can be seen. If there is no observation, we're going to just write no change, and where reagents are used, correct names and formulas must be given. If any solution is warmed, boiling tubes are used, and if a solid is being heated, hard glass test tube apparatus must be used. Must rinse and reuse test tubes and boiling tubes where possible. No additional tests should be attempted. Let's look at 3A. So it says we have a bottle labeled Fa5 and it is thought to contain hydrated zinc sulfate. Therefore, it should contain zinc ions and sulfate ions as well as water of crystallization. It's asking us to devise and carry out tests to investigate whether these three are present. We should record the tests and carry out and make any observation or note down any observations we see in the space provided. Okay, to see if we have these ions, we need to carry out a series of tests. So what we're going to do is we're going to take our solid, and if we heat our solid and we end up with condensation, that means we have water of crystallization present, right? Because it would evaporate and condense. Then what we would have to do is we're going to have to dissolve our solid in water to produce aqueous solutions. So we can carry out further tests to identify whether we have zinc ions and sulfate ions or not. We could take a portion of our aqueous solution and add it to aqueous ammonia. If this produces a white precipitate that is soluble in excess, then we certainly have zinc 2+ ions. Then we can take another portion of this solution, add it to our barium chloride. If a white precipitate is formed, then that means barium sulfate was formed, and we have sulfate ions. However, this isn't just the case with sulfate ions. This can also be the case with sulfite ions. And to distinguish between the two, we're going to add hydrochloric acid. If our white precipitate is insoluble in a hydrochloric acid, then that is for sure an indicator that sulfate ions are present. Now, during this practical and according to the mark scheme, the step number 3 here was actually insoluble. So you would say that obviously you'd be given the solutions, you'd be given the solid and it would actually have zinc ions, and then you'd find that it's insoluble. This is indicated that there isn't zinc 2+ ions, but rather Mg 2+ ions. Really what you would need for the 5 marks that this question is worth is all 5 of these points alongside your observations. So on that note, according to the mark scheme, sulfate ions were present, water was present, zinc ions weren't present because when we carried out step number 3, we ended up not having solubility in excess. Okay, for these next two parts, they're really just observations, but basically you have crystals of a unknown solid, and then you have to heat it in a hard glass test tube. It states that until no further gas is evolved, you must heat it, so there is a gas evolved. So you just think of your tests. You can use a glowing splint, and it would relight, meaning it's oxygen, but it's really just about observations, not really identifying. Mention of the starting color and then the end color of the residue gains you marks. It's only worth 2, so any 2 points are good enough. Stating that there's a gas is not enough, and the solid jumping around is a good observation to make as well. Right, then here it says the residue that is cooled. It asks us to add approximately 3 centimeters of water to it, filter the solution, and then tell us what the color is, and it turns out to be green. Okay, then it says it's given us 3 solutions. Fa7 is an aqueous solution of Fa6. All these solutions are compounds of one metal that has different oxidation states, meaning it's going to be a transition metal. Carry out the following tests and provide your observations. I don't have the equipment for this. I just copied down the mark scheme, and I think just general advice would be to always test your gases and write as much as you can, and precipitates upon dissolving, what happens, so and so, colors, and try to fill in as much as you can so you can gain as many marks as possible. Then it says to complete the table and identify the metal. I think it's a lot easier to go with actually, technically, we could do both at the same time. So if you go to the end of your paper, there's actually a table, and if you look at it, we do carry out a test with sodium hydroxide right here. It's also present here. Right here. So as you can see, the observations we got were off-white precipitate and then brown precipitate on standing. And this aligns with this one right here for manganese 2+. So this must mean that Fa8 is manganese 2+. Right? So, meaning the oxidation state is +2. Therefore, the metal is manganese. And then Fa6/Fa7 must have an oxidation state of +7. Why is this? Because when manganese +7 is reduced to manganese 2+, there is a color change that is shown right here from purple to colorless.